two vials show the start and end of a massive industrial transformation. On the left is the cloudy, raw juice squeezed from the harvest, and on the right is the final 99% pure crystalline solid. In its initial state, this juice is a volatile soup of plant matter and organic impurities. If you simply apply heat to boil the water away, the impurities cause the entire batch to caramelize and burn. Surviving the journey to that pure white state requires a 5-stage gauntlet of chemical reactions, vacuum thermodynamics, and over 1,000 Gs of centrifugal force. Refineries treat sugar as a precision chemical solid, using industrial engineering to force a chaotic organic liquid to obey strict physical laws. The first problem is chemical. As this diagram shows, the incoming raw juice contains dissolved plant proteins that make the liquid dark, murky, and chemically unstable. To stabilize it, operators apply heat and a precise AI-regulated dose of lime. This triggers a specific reaction across the entire tank. This is flocculation. The lime molecules bind to the proteins, forcing them to clump together into heavy, solid masses called flocs. While the impurities are still in the tank, their state has changed. Engineers have successfully transformed a dissolved, invisible threat into a controllable physical mass. But even with the impurities clumped together, you still have to remove them from thousands of gallons of liquid. The mechanical solution is the clarifier, a massive vessel designed to weaponize gravity and settling times. In this cross-section, the heavy mud flocks sink to the bottom hopper to be scraped away. Simultaneously, the purified liquid rises and is siphoned off the top. This separation results in a clear state change, from murky to golden. But the juice is still 85. Water evaporates at 100 degrees Celsius, but at that same temperature, the sugar in this juice will caramelize and burn. To solve this, refineries use multi-effect evaporators. These linked chambers recycle the vapor from one stage to the next to maximize energy efficiency. The engineering trick is manipulating atmospheric pressure. By creating a vacuum, the boiling point drops to just 70 degrees, allowing the water to evaporate without burning the sugar. This pressure shift safely concentrates the thin 15% juice into a dense 65% syrup. Next, that formless syrup must be forced to build uniform geometric structures. This happens inside a vacuum pan, where the syrup becomes a thick, bubbling mixture called massaquite. To initiate the growth, a robotic needle injects microscopic seed crystals. This process, called nucleation, gives the liquid a physical blueprint to build upon. Once seeded, the surrounding syrup begins attaching itself exclusively to the geometry of those nuclei. AI sensors manage the saturation levels until each crystal reaches its final form. We have solid sugar, but it is still encased in a dark, sticky byproduct that must be stripped away. These new crystals are completely trapped in a matrix of thick molasses. They are chemically pure, but physically contaminated. The final isolation requires a high G centrifuge. This machine spins at 1800 RPM, creating enough force to rip the mixture apart. Rotating at these speeds creates over 1,000 Gs, enough to force the molasses through a 0.5 mm mesh, while trapping the solid sugar inside. A final high-pressure wash strips away any remaining microscopic film, polishing the crystals before they are discharged. It took chemical and thermal precision to grow the sugar, but it required brute kinetic force to achieve final commercial purity. These stages show the path from an unstable, swampy liquid to a bone-dry, 99% pure solid. Refining sugar means navigating these physical and chemical barriers with industrial precision, turning a harvest into a shelf-stable solid. This diagram illustrates a highly specialized industrial pipeline. Its purpose is to synthesize high-value combustible fuel, specifically ethanol, deep inside a state-of-the-art bioreactor. But before we get to the fuel, we start with this: raw sugarcane or beet molasses. It is a highly viscous, nearly impenetrable sludge. This schematic reveals what makes that sludge valuable. Trapped inside are high concentrations of fermentable sugars, like sucrose, glucose, and fructose. However, the gray rock-like structures are non-sugar impurities, mostly ash and gums. This dense concentration makes the raw syrup entirely unfermentable. You cannot just drop yeast into that sludge and expect it to survive. we have to meticulously chemically engineer this raw material into a perfect biological environment before any fermentation can actually begin. This tank diagram shows the very first step of that conditioning, breaking the physical viscosity. By heavily diluting the molasses with water, the thick mash thins out enough so that it can be pumped, mixed, and metered. This refractometer readout shows the precise target of that dilution. We're aiming to bring the total sugar concentration into a viable range of 13 to 22% Brix, the exact specific gravity needed for yeast to survive. This nutrient enrichment diagram illustrates the next requirement. Yeast are living organisms that need specific nutrition to thrive and multiply. To remedy natural deficiencies in the molasses, engineers directly inject nitrogen and phosphorus straight into the steel mixture. But creating this nutrient-rich, sugary liquid introduces a biological threat. Competing lactic acid bacteria thrive in this exact environment. If left unchecked, they will eagerly consume our freshly conditioned sugars. This acid injection schematic details the countermeasure. Engineers drop the pH level of the entire tank down to a narrow bracket between 4.5 and 5.0 by injecting sulfuric acid. This specific pH bracket creates what is effectively an acidic shield. It forms a chemical environment that suppresses the competing bacteria while leaving our specific strain of yeast completely unharmed. This UI dashboard clearly compares the before and after. Through precise dilution, nutrient enrichment, and targeted acidity, the previously hostile raw material has been perfectly conditioned. Industrial chemistry is the prerequisite for biological yield. With the environment prepared, we run into the next logistical hurdle. To process tens of thousands of gallons of mash, we need billions of biological workers. This requires vastly more yeast than a standard inoculation provides. This step-by-step scaling diagram shows how engineers solve the volume problem through a process called the seed train. The yeast copulation is systematically grown and transferred through successively larger industrial tanks, expanding its numbers exponentially at each stage. To achieve that rapid scale-up, engineers employ a specific environmental hack. They constantly force massive amounts of dissolved oxygen into the system. This aerobic diagram shows exactly what that oxygen does. It triggers aerobic exponential growth. By flooding the tank with O2, the yeast prioritize pure cellular reproduction, rapidly budding and dividing rather than producing alcohol. By providing an unlimited supply of oxygen, engineers successfully hijack the organism's natural life cycle, rapidly building a massive workforce ready for the main event. Now we transfer our newly cultivated yeast army into the main fermentation vat, which is already filled with our chemically conditioned mash. This convergence diagram shows the physical shift in the process. Once the yeast is loaded in, engineers seal the massive system and entirely cut off the oxygen supply. This side-by-side UI tracks what happens next. The lack of oxygen initiates a metabolic switch, shifting the yeast into an anaerobic survival state. To generate ATP, their cellular energy currency, they begin to aggressively consume the conditioned sugar surrounding them. This chemical engine diagram details the exact result of that starvation. As the yeast metabolize the glucose to stay alive, they continuously eject ethanol and carbon dioxide as their primary waste metabolites. The system uses deliberate oxygen starvation as a tool. It turns a microscopic organism's biological panic response into a massive industrial engine. This anaerobic engine runs continuously, undisturbed in the sealed vats for 24 to 48 hours. This final yield diagram shows the end result of the timeline. The once unfermentable, viscous sludge has been successfully converted into a liquid known as beer, which carries an 8% to 12% ethanol concentration. Modern industrial ethanol synthesis succeeds by turning the fundamental survival responses of nature into a manufacturing engine. By feeding, multiplying, and then starving billions of yeast cells, engineers force a biological panic that results in high-grade fuel.